Welcome everyone to this panel. We are pleased that four gentlemen who are guests here did a favor to us to join this panel, Matt, John, Pete, and Rodney. They will in a few seconds introduce themselves. I am Ivan, I'm partner in McKinsey. I lead our Global Technology Council where we look at emerging technologies, and I'm in charge in Quantum. And besides that, I'm thinking a lot of time about innovation and how the technology can drive innovation for industries and countries. So shortly, what we plan to discuss today during this panel is three things. So one is the views of our guests of the current state of quantum computing. The second one is a little bit speculative, but we'll talk about the technology roadmap. And then we will spend some time talking about the enablers, ecosystems, investments, and so forth. So these are big three themes. I would just like to do a short intro before I pass it to our members to introduce themselves. And essentially, the intro will be around these three topics. So what we were doing in our technology council that has many external members, more than 30 when it comes to quantum already, we were actually doing specific industry workshops and looking which use cases by industry, and these are just illustrations, could actually, where quantum could bring business value. So we were going business back, not necessarily technology back, and we mapped a number of these. And then linked to that, we actually aligned on a nomenclature and the roadmap for quantum computing, starting from not fully error-corrected to fully error-corrected quantum computer or even quantum supercomputer. And we are trying to align the use cases versus these eras and quantify what value at each stage will happen. And then the third thing, we are looking actually at the dynamics. And we just published a Quantum Monitor. We're looking at investments, the number of startups, and also the patents. And what we can see, it's a huge acceleration in recent years. So we are starting to see this dent of exponential curve. And also, many countries are ramping up their public or continents are ramping up their public investments into quantum. So a lot of interest and momentum. But in order to sustain that interest, I think we will need to sustain the investments. We will need to be able to bring community. There is a gap in talent, and we will need to upskill a lot of people, standards and accessibility and integration. So that whole report will be released publicly together with all following materials like use cases and evaluations. And we're looking forward to that. And in the wake of that, what we were intending to do today is to bring some of the people who are in the first lines driving this innovation to discuss a little bit around what are their views on these topics around the three themes. So before I start with the first question, I would just like to ask our panelists to introduce themselves, although many of them are familiar to you. So maybe we can start in the way I'm seeing people on the screen. So Matt, maybe starting with you.
Hi there, I'm Matt Trevithick. I'm the Chief Operating Officer of Google Quantum AI. I'm based actually in the company's headquarters in Mountain View, California, but our quantum hardware efforts are in Santa Barbara, California, and our quantum software efforts are based in Los Angeles, California. So we're kind of a West Coast of the US centric organization. I have to say, Yvonne, thank you and your colleagues at McKinsey for convening this panel and for really investing your own resources to research the quantum computing industry. It's been a pleasure working with you, your colleagues, and the other panelists here over the last several months to pull together this report. And we look forward to seeing it published in the next few months.
Yes. Thank you, Matt. Thank you for doing us a favor to join here. Over now to Pete. Pete, you're next on my screen.
Hello there, I'm Pete Schabel. I'm a co-founder of PsyQuantum. We're a startup based in Palo Alto. And yeah, my background is that I've spent 10 years on the hardware and software of quantum computing, principally as a technical person, and then doing all sorts of things since we founded the company and moved to California. And yeah, it's a real pleasure to be on this panel. Thank you, Ivan, and to the organizers.
Rodney, you're the next on my screen.
Sure. So hi, I'm Rodney Zemmel. I lead McKinsey Digital, which is the part of our firm that helps clients on digital AI and technology globally. I'm excited to be here, and I'm joining you from a sunny New York today, so I'm feeling the lone East Coaster on this very West Coast group.
And last but by no means least, John, just over to you.
Yeah, thank you. I'm John Martinez. I'm professor of physics at UC Santa Barbara. I've been working essentially on superconducting qubits since the mid-1980s. And I had worked at Google for about 7 years, ending about a year ago today. And kind of the culmination of that work at Google was to kind of be a leader of the project to do the quantum supremacy demonstration.
Great. And that intro just brings me to the first topic. So I will start with that. Before that, I just want to ask audience, feel free to ask the questions in the chat. And we might even have some questions verbally for you. We will actually play back the questions as well as we go. So to start with, you started with quantum supremacy. So the question to all of you, it's a little bit broad, and then we can go into specifics. So what can we actually do today realistically with quantum computers? And then the second question to that is, how useful is that, or how useful it will be relatively near term? So maybe because John, you spoke about quantum supremacy, and I know you have a particular view on that. Maybe we can start with you, and then we could do a round to Pete and Matt. And I reserved a special question for us.
Sure. People have been talking about the potential of a quantum computer for many decades now. And while we are at Google and building up these systems, we decided it would be nice to show the power of a quantum computer for at least one problem, a crafted problem, even if it's a little bit mathematical. And that's what the quantum supremacy experiment was designed to show. That a crafted problem, you would run quantum computer for 200 seconds. And if you wanted to check it, it would take thousands of years on a supercomputer. And thus, you would check that and show the power. I think more importantly, it was able to check that the quantum computer was working properly, that there was no unknown physics that would prevent the quantum computer from working. And in fact, we were able to match the error rates of the system versus the error rates of individual qubits and gates to show that things were working properly. So both from the practical and in very fundamental point of view, that was an important experiment to show that the theory behind this is working properly. Now, of course, to do something useful, you have to do a more complicated algorithm, and that's what people are working on now. And they have to build better quantum computers. We have to understand how to more efficiently run and come up with algorithms. So there's a lot of research right now, both experimentally and theoretically, to bring the field to not just a powerful stage, but a useful stage.
And maybe just logically moving to Matt, because essentially you took the supremacy experiment and you announced a lot of partnerships now. So Matt, I mean, where are we today, and what's the hype versus reality? What can we do?
Sure. Well, let me just first take a moment to thank John Martinez for all his contributions to Google and to our team. We're deeply grateful for that. And really that experiment we published in 2019 took us into the realm that we call a beyond classical realm. And that really is the driving force between our team. Once you get past about 50 physical qubits, you start to get into the space that no simulator can match. So while Google and others have open source simulator offerings that allow people to experiment to that level, really our team is trying to drive beyond that. So the question that I wanted just to pose to the audience, because I think it's really important to our industry right now, is what can be done with a few hundred noisy physical qubits that cannot be done on 30 or 40 idealized simulated qubits? Because Google and others are going to have on that order of a few hundred qubits available as a service offering, in the next couple of years. And so that is really the sandbox that we're now playing in. And we're very interested in all the ideas of what can be done there. So, I'm really happy Pete follows next, because I think he's got a really great answer to this. But our question is, what useful things can quantum computers do over the next decade while we wander through this noisy intermediate scale quantum era? There's lots of things that can be done once you have a full error corrected quantum machine, but an existential question for many of us is what can be done before that happens. And with that, maybe over to Pete.
I think Pete will have a view on that.
Yeah, so thank you again for the opportunity to speak today. So yeah, first of all, quantum supremacy is really an incredible scientific milestone that I've been waiting, personally nearly 10 years to see. And I want to thank the team, John and the team at Google who did that work, because it's just an incredible and super exciting validation of what we're doing. You got to remember, this is a chip that's a little bigger than your thumbnail that really seems to win a race with a building-sized supercomputer. That's absolutely thrilling, right? That's why I'm doing this in the first place. But on the other hand, it's not doing anything that's kind of commercially valuable or solving real problems today. And I think it's really important to emphasize, because it's sometimes hard to tell, today there are no quantum computers that do anything useful. We don't have one. Nobody out in the world has a quantum computer that is doing something that's really worth like serious money. There are machines that run code and that give the right answer, but for problem sizes that are not yet interesting. And yeah, we spent 10, 15 years at the University of Bristol playing around with small optical quantum computers, doing things like, super miniaturized demonstrations of Shor's algorithm and quantum chemistry, variational quantum eigensolvers, all of this kind of stuff. And it's very fun and you can publish lots of papers. But when we founded the company, it was with the understanding that, we took a very extreme position, which is not shared by some of the other players, which is that you're probably not going to find anything useful to do until you've got error correction. That all of the algorithms that we know of today require billions of serial gate operations, and you're not getting billions of gates without error correction. And so, it's absolutely conceivable that NISQ works out and that we find something to do with 100 or so qubits and no error correction. It's very hard to prove a negative, and the jury's absolutely out on that one. But we've taken a path that says, look, we're not going to have any commercial applications running on hardware until error correction kicks in. And yeah, so that's an extreme position, but I'm glad that we've taken that path. Yeah. But again, it's really important to emphasize there's lots of quantum computers that are doing things and giving the right answer, but none of them today are doing anything that's really worth money.
Thank you. I don't know if people just want to reflect on that, because then I would avert the one question to Rodney before we move on. John.
I wanted to make several more refined points on this. If you build a quantum computer with 100, 200 qubits, and right now the 2-qubit error is about a 1%, maybe a little bit of 0.5% error on that, and you have 200 qubits, you can basically do one logic operation per qubit before the whole system loses its memory. Okay, so although you might be able to find a NISQ application, this seems somewhat unlikely that you're going to do it. And in fact, I think a better metric and better utility metric right now is to make the quantum computer better and lower errors and not necessarily make more qubits, although one could debate that. But let me say what's really good though, even though people are, I said that, even though people are making big machines and putting that on their proposals, I think it's really healthy that they're doing this, because you have to build these big machines to know all the system engineering constraints and to test your qubits and to know if everything's working okay. So from a system engineering point of view and just getting everything working, building these big machines are great for testing. And I think that's the real value of these NISQ machines in the next few years is you'll further test them. Since that was what the quantum supremacy experiment was, you'll continue to do that. And then you'll kind of know you're on the right track to say eventually build an error-corrected machine.
Okay, so what you're saying, John, and thank you, I just want to synthesize, and we like that. So the next era is more de-risking technologies and finding proof point, as opposed to, you know, immediately jumping to.
You can say that. And I'm going to say that a forefront of this field is understanding the systems engineering, the quantum systems engineering, and you have to build the machines and learn what all the problems are in order to properly do that. You have to be testing these machines. And I think it's very healthy now that we're testing a wide variety of different physical systems, and then we'll learn what to do next.
And Ivan, just to riff off that just quickly here, we're entering a period of application discovery. And what we're enthusiastic about at Google is that now that we actually have quantum hardware that is beyond classical, there's a motivation for programmers to figure out what to do with it. So we're kind of, optimistic around the serendipity that exists around lots of clever people figuring out what to do with hardware now that it finally exists. And what John says is absolutely right. You need these large systems to be able to tune them and tweak them, find their strengths, their weaknesses, and ultimately, get towards a valuable application.
And the quantum computers are now powerful enough that you can run algorithms with thousands of gates, and you can really test them not in a trivial, just science way or business, but you can really test them in detail given the complexity of the gate sequences and learn how to make things better. And I think there's a real excitement now because you can do these much more complicated tests.
Great. Thank you. Now over to Rodney in this first segment. Rodney, we are seeing much more kind of industry, and in particular, you're talking to a lot of executives and in different forums. So where do you see two things? One thing is the question more, where do you see most interest for applications today when we talk to the clients? And then the second question, to shoot it out immediately so I don't interrupt later. I mean, you went through the era of AI since maybe 2010 to today, and we still talk about capturing value. So the question is, if we compare the hype cycle, how does the pattern recognition look like? Where are we? So these are two questions for you, Rodney.
Sure, and maybe I'll start on the second one actually. So where are we in the hype cycle? It's sort of the ultimate, like, can you call the market, right? And if none of us can call the housing market, our ability to call the quantum computing market is probably pretty limited. But I do think it's helpful to argue from analogy, and actually an even better analogy than AI is actually biology and the Human Genome Project. And look, it's only an analogy, so it has its limitations. But if you think about the early days of that project, late 90s, so late 90s before it was completed, it was a hardware race, right? And people were talking about quantitative metrics and whose hardware was better. It was a race between private companies who, at least one private company, that thought they could do it themselves twice as fast as a government consortium. And then it was a race between academic institutions who were debating between doing it independently versus doing it with pooled resources. And it took all of those things together to actually get to, I guess, just a little over 20 years ago now, like the first sort of draft map of the full human genome. And people thought that was the end of the race. And the reality was that was the beginning of the race, because it was only after that that really the application started to develop. And that feels to me like where we are now, right? So Ivan, the chart you presented a moment ago with a 75%, 74% CAGR in investment in quantum is incredible, right? There aren't many places with that level of growth rate in investments. If you get underneath that though, the vast majority of that, more than 80%, is going into hardware or even hardware components, right? Which is of course what you need to unlock the opportunity, right? But this will be further along when you see as much effort going into sort of the software and application layer, which is an area of massive sort of startup interest now, but it's not yet getting the same level of broad support. When you see real service businesses evolve, and Matt obviously talked about one that Google is looking to launch, And then when the real end users are seeing value from it, right? And it really, you've got to see that end user value, as Pete was saying, to pull through all of the rest of those the steps along the value chain. So then if I flip to the first question you asked me, which is where is the end user value? I mean, honestly, if you have conversations with across different industries now, it's all over the map, right? I'd say there's general excitement and there's general recognition that sort of, the mega problem of, can you really change how people think about encryption, right, is out there. But there's many other problems along the way that people are interested in. And I would say in every sort of science-based industry, there's an opportunity. And maybe this time I will use an analogy from AI. If you look at the early applications of AI, it was not actually solving the unsolved problem. It was solving better, it was optimizing problems rather than new problems. So probably 70% of this at the beginning is going to be about optimization versus brand new problem. But if you want to be exciting for a minute and go to the brand new problem, right, 4 or so that I think, Ivan, we're going to cover in the report just as examples, right? So look, everybody talks about catalytic improvement, right, with nitrate synthesis as being, or improving the Haber process as being one on there. We were joking that's kind of a relatively old-fashioned and unsexy application of maybe the world's coolest technology, but it's a 40 billion or more market opportunity. Charge transport modeling, right? So anyone who has a screen that requires charges to move around, so the iPad that I'm talking to you on, or anyone who's in the battery technology business, that's at least a 5 billion market opportunity, potentially much more. Big pharma is one of the industries that's taking this most seriously right now, and not just the protein structure solving, but protein-protein interactions. If we could really get ahead of that and really understand that better for drug discovery, who knows, but that could be a $100, $200 billion market opportunity. And then telecoms is another industry I'd point out as being very, very far along. And telecoms companies are among the biggest capital spenders on the planet. And how to actually optimize your capital spending in telecoms is a hard network optimization problem of the sort that could be tractable to this. And that's a $50 to $70 billion market opportunity at least. We could get into other even cooler ones, how you replace GPS and so on, and that's at least a 30 billion opportunity. It's a long, long list.
Thank you, Rodney, so much for your answer. I will just slot in 2 more answers. We still have 20 minutes and some things to cover, but there were questions from the audience that I want to feed in here that fit well. One was to Matt from Alex. Where do you specifically see the largest benefit of quantum computing for AI, Matt? And then there is one question for John.
Sure, Ivan, I'm happy to take that one. And thanks, Alex, for the question. So as Rodney just articulated very well, we believe that quantum computing is going to be a very big deal in the 2030s, so 10 years from now. It's a very big deal, and that's why Google's investing heavily in the space. We believe that quantum computing will provide new computing capabilities that sit on top of the very large and existing market for classical computing capabilities. So not necessarily going to compete with classical computing directly, but in a complementary way. So to answer the question specifically about AI, we think that quantum computing will act as a co-processor to the existing classical implementations of artificial intelligence. One example I like to use is a lot of artificial intelligence relies on big data, the processing of very large amounts of data. Presently, quantum computers have relatively slow input and output. And so that's unlikely to be an early application of them, but they can do other things such as detect patterns and, as Rodney said, optimizations that may be very useful to some AI algorithms. So the short answer is quantum computing will be a co-processor to classical computing for AI for the next decade.
Thank you. Thank you, Matt. And now I will shift us to the second topic, which I know John will say it's speculative, but there's also one interesting question for you, John, but I will start this time with Pete. So Pete, how do you see the tech roadmap? And I know you have distinct view from others, so I just want to recognize that, but how do you see the roadmap evolving? And there was actually a question for you linked to that. whether from Jan Blumart, whether you see gradual improvements toward QEC, or you are just really thinking of a straight, fully error corrected. And then I will ask the same question back to John and Matt, but I just wanted to ask you, Pete.
Yeah, so thank you for the question. I think first of all, let me say that I'm very glad that the field of quantum computing is diverse and that there's a lot of people pursuing lots of different approaches and lots of different strategies, because it's very hard to build a quantum computer and nobody knows who's going to win. And we better have a bunch of bets on this technology. PsiQuantum has taken like a very extreme position. So what we're doing is by design and happily distinguished from perhaps what other people are doing. So I think if you look at the kind of the median technology roadmap for a quantum computing company, especially a hardware company, typically that starts with a handful of qubits up and running on a chip somewhere. And then you'll go and put that chip on the internet. So hook it up to AWS or Google Cloud or similar. And at some point in the near future, hope to have a NISQ machine with 100 or so qubits, a relatively low error rate. And you're kind of betting that you're going to have algorithms per Matt's question, which of course we could absolutely find. And you're going to run those algorithms on 100 non-error corrected qubits or so, and make some money that way, use that as a stepping stone. And then somewhere further down the line, you have an error corrected system. And we can talk about the intermediate milestones between those 2 points. But the holy land of a large scale error corrected machine is at the end. What we have done is to build a roadmap for ourselves that skips that NISQ regime. So from the very beginning, we said, we're not going to do that. We're just going to spend all our time and money shooting as fast as humanly possible for the end zone. And if you look at what the intermediate milestones are on that trajectory, they're not small quantum computers, right? So our trajectory, we're not building, a small quantum computer and then a slightly bigger one and a slightly bigger one. Where we spend most of our money and time is really semiconductor manufacturing. So there is a night and day difference between the types of experiments that we used to do in the university, which are built in a unscalable fashion using kind of hand assembled systems, and the thousands of 300mm silicon wafers that we are now building at global foundries in upstate New York. And it's frankly a lot of work to go from the former to the latter. And really our big milestones are in terms of enabling new manufacturing processes in a regular silicon chip fab. Because these fabs are capable of building very, very large numbers of components. They're the guys who put 1 billion transistors in your cell phone. It's kind of a promise that if we want to build lots of components, we can do that. And yeah, our technology roadmap, the major milestones are really about enabling new manufacturing processes in that fab. So it's challenging for us to have to tell people, no, we don't have an interim milestone that's a small quantum computer, but we are betting that that's going to allow us to go faster to the end zone. Yeah.
Thank you, Pete. Matt, I think you have a bit of a different strategy, so maybe you could also have and then I would pass to John.
Terrific. Well, first of all, I believe and Google believes that the entrepreneurial community, will be incredibly important to the development of quantum computing, both on the hardware and the software side. And I have to say, Pete, we're incredibly impressed with what you and your colleagues are doing and the clarity of your vision. You make the whole industry stronger because of that. What Google and others are doing that are pursuing superconducting qubits, we've all seemed to have converged upon a similar timeline. When our team revealed its 10-year roadmap last July in a video that everyone can access on YouTube, we basically established this roadmap for getting to an error-corrected quantum computer by the end of the decade. It was very interesting that about a month after that, a Chinese group proposed a very similar roadmap. And a month after that, IBM published their almost identical roadmap. And so there seems to be a coalescence now around the intermediate milestones getting to an error-corrected quantum computer if you're using superconducting qubits. The reason we are taking this approach is we believe that this has the highest probability of success to getting us there. So we're very secure in our approach, but we applaud the efforts of PsiQuantum and other startup companies that are challenging, call it conventional wisdom, and are hoping to get there in half the time with less money. A point I'd just like to end on here is what Rodney said. There's going to be an enormous market in quantum computing software in the 2030s, and probably like as in other areas of computing, the software market may actually be more valuable than the hardware market. So that's the promised land we all want to get to. So whether we get there with electrons or photons, history will determine. But the important thing is that we as humanity get there.
Yeah, or both, right? It's rare that there's just one technological solution to this kind of problem.
And that brings me to John quickly. Then I have a question for you, Rodney. John, I mean, you are kind of now helping really entrepreneurs and others to build better quantum computers. So I know you have a view that this is speculative, which is true. But do you have a perspective on this sort of roadmaps and where we are, how to accelerate?
I would just say that building a quantum computer is hard, as other speakers had said, and it's very good. We have different technologies and different viewpoints on how to do it. And I think it's very good that there's some good resources being put into it so that we can do a serious engineering job right now. I think it's, there are serious challenges. There's lots of unknowns that we have to discover and get by, and we'll just have to start building the systems and see what happens. And again, I think the whole the quantum systems engineering and understanding all the problems that kind of come about when you're building a complex system is a real forefront of the field. And I think with all the investment going on, we have a chance to really tackle that and figure it out. We just have to build it and see what happens. My intuition is that these are hard machines to build, and instead of having lots of machines out there that'll work, it'll narrow down to a few, and hopefully that number will be greater than 0. Okay, but we'll all work hard and work hard to make this a reality. And there's lots of good ideas out there.
Rodney, thank you, John. And Rodney, just a quick question to you. Now, John mentioned, and I know, Matt, you also have a perspective on this. So first to Rodney, John mentioned, the investment. And if you look at the investment in hardware here, there's certain probability, technical probability of success. It's going to be capital intensive and number of years until the full payoff. So how do you see some analogies of this, investment cycle and general comments as we saw this kind of exponential take up? And then I know, Matt, you have a sort of a perspective on this. So I would also ask you to answer after Rodney, if possible.
Yeah, so this is different from a lot of other technology waves in its capital intensity. Maybe here, actually, the closest analogy might be telecoms networks, right? The money needed to create different networks in different geographies, right? And that level of capital intensity, I mean, there's only going to be so many companies that can really afford it. And I think where you're going to see sort of a more robust startup ecosystem is either going to be around software and services to those larger companies. It's going to be around a few bigger bet sort of startup type investments, and obviously we're seeing the average check size in venture go up quite a lot. I think in part driven by capital intensive opportunities like this one, but also there's a big role for government here, right? And I know it's not our job to talk about government policy, but it is interesting that there's at least 7 countries now that have put or claim to have put close to $1 billion into quantum. And some of the attempts to create real collaboration between different institutions, whether it's private, university, and government. I'm very interested in what the Chicago Quantum Exchange has been announcing, the incubator that they announced, and the way they've got private universities and government research labs working together. I think it's going to take more of that, certainly to accelerate things, but maybe also, to John's point, just to spread the risk a little bit, right? This is a world of high uncertainty, and you're going to need a little bit of a sort of a pre-competitive safety net to incubate a few more different bets.
Matt, you had your background in VC, and I know you have a view on the capital, on specs, on everything. So whatever you're comfortable to comment, but I would ask similar question like Rodney, both on capital intensity and the views on the current wave.
Sure. Well, I think John Martinez said it very well. Building quantum computing hardware is hard. It's very hard. So the actual question ends up being, how many highly qualified scientists and engineers are required to pull off this engineering feat? And because humanity's never done this particular feat before, we don't actually know. We have to estimate. And so just one way to set some error bars on this are, it takes about 200 scientists and engineers to develop a new silicon-based microprocessor, if the team has done it before, and if they're standing on 70 years of a semiconductor industry. And I just checked the numbers here. SpaceX now employs about 10,000 people trying to colonize Mars. So we estimate that building a quantum computer is somewhere in the middle of those technical difficulties. It's going to be harder than building a silicon processor, because we have to not only build the quantum processor, but we have to build up a supply chain around that. So you may estimate it'll take a few thousand people to develop a full quantum computing system. And so then one has to ask themselves, how much money will it take to convene a team of that scale and caliber for as long as necessary to build the quantum computer? And so if you use our 10-year framework, you might say a decade. So I think Rodney's correct to say there's going to be a limited number of organizations globally that can convene that, rare talent pool in sufficient quantities for long enough to build a quantum computer. And so whenever I look at a project like quantum computing, I think you do have to look at the entire capital required to get to the promised land that Pete said. And financial risk will be a major, if not the major, risk that these projects take. I honestly believe that with the foundation we have, given enough money and time, scientists and engineers will be able to figure out these problems eventually. And so I think we are already in the quantum era and should be thinking about that. But I echo a lot of what Rodney said. These are not short, inexpensive projects.
And actually, just to add on Matt's comments, right? Talent is going to be the scarce resource here, even more than capital. Right? It takes a lot of capital, but the world is not short of capital for big projects right now. But qualified talent in the quantities needed to drive this, it's going to take a lot of investment, education to really create that flow.
Pete, I want to give you a chance to reflect. You seem to have some ducks in a row on this, but maybe one short reflection from your side.
Yeah, no, I think I actually would really echo what Matt said here, which is I've never started a company before. I've never had a real job. The only real job that I've ever had is working in a garden center, stacking pots. So I've learned a little bit since I came out here to Silicon Valley. And one of the things that you learn is how much things cost and how many people you need to run a project. And yeah, the arithmetic is pretty straightforward. Like, it's going to take a very long time to build a quantum computer that really does something useful. We're willing to be optimistic, but it's not happening tomorrow. And you need a ton of people, and you need to turn a lot of silicon. Like, you need to go through hundreds of thousands of wafers worth of silicon probably to get this thing built. So yeah, it's going to be very expensive, and we are in a very, very fortunate position. We have a lot of responsibility on our heads. in light of the wonderful funding that we've got. And yeah, I think the field needs to think long and hard about how we're going to bridge the gap to that endpoint. It's a very, very challenging problem. Yeah.
Great. Thank you, Pete. I have one last question because we have 4 minutes left, and there were some questions for the audience, but we will follow up and answer if you don't get to it now. But for me, the question is really kind of zooming out and thinking about big picture. So for each of you, and I will start with John, is really what can like the community. Rodney started talking about governments. We exchanged some ideas on grand challenges and other things. So what can community do to accelerate the whole field? And when I talk community, I'm talking about the whole ecosystem from the end user, companies, etc. And especially, given that quantum can solve some really pressing problems for humanity, at least we in this panel believe. So I would just like to that's an open-ended question, but a bit provocative. I just want to hear your thoughts because that could move some action.
That's a good question. I think what's happening now is for superconducting qubits, we have a system that's working, but we have to make it work better, okay? And we have to get the errors down. And there's a lot of interesting research going on there, but because of the kind of competitive nature, everyone's doing their own thing and not necessarily communicating as effectively that they could be. So I think if there was a little bit more communication and exchange of ideas on some of the coherence and fabrication issues, which are kind of a little bit pre-competitive, just so that people can learn how to make good qubits better, then I think everyone will do better, and then we're more likely to build the machines that we need to. And then the competition maybe is going to involve around how to scale and some of the software and control and other things. But I think really figuring out how to work together more effectively would be good.
Thank you, John. Matt?
Yeah, so markets need both supply and demand. And I think what would be really beneficial if we saw stronger demand signals from the market that get very specific about how performant does a quantum computing system need to be in order to solve a valuable problem. You touched upon the point of grand challenges, and it would be wonderful if the community could come together and maybe settle on a couple of grand challenges, right? It might be a new battery chemistry. It might be, a new approach to carbon sequestration. We at Google happen to believe that quantum computing will address some of the, matters of climate change. But if a demand signal could be created, that would give us a target to shoot for. When we talk about getting to a useful quantum computer by the end of the decade, right, it certainly echoes, the early days of the Apollo mission where we're going to get to the moon. But where the Apollo mission had a great advantage is the moon was such an obvious target, and smart people could figure out exactly how powerful a space system you would need to get there. And I think if we could coalesce as a community around a small set of targets to go for, that would be a much more interesting metric of success than quantum volume or any other type of a very technical metric that is being pushed by the supply side. So let's get a demand signal here. Call it a grand challenge.
And hey, Matt, if I can follow on to Ivan's question, actually, what would the characteristics be of a good grand challenge for the field?
Yeah, and Pete's got some good comments on this, but it's basically doing the hard work to figure out exactly what kind of quantum computing resources would be available. How many qubits do you need? What do the error rates need to be? What are the number of gate operations? If we could actually, crystallize it into the metrics that the scientists can build towards, that would be extremely helpful. And maybe I'll hand it over to Pete now for the final word on that.
Yeah, I would just second both of those comments. So absolutely, John, I think that, this is a technically extremely broad challenge, and we're all solving similar problems, even though we're pursuing different technologies, whether it's in error correction, packaging, networking. There's a ton of overlap, and there's a huge advantage to be gained if we can engineer some collaboration. And then, yeah, to Matt's comment, I'm sure there's a lot of people on this call who are in the situation of thinking that quantum computing is awesome and having some ideas as to where it might help in your business, and not being able to articulate exactly what speed up you're going to get for exactly which problem under exactly which circumstances. And unfortunately, it takes a team of like 20, 30 people working really hard for many years to go from the former to the latter. And teams at Microsoft and Google and in academic groups around the world have done this, a handful of times, but to really take a single problem, narrow and very deep, is a serious undertaking. And I think, the field would benefit from a lot less kind of, hey, quantum computing is awesome, we can apply it to everything under the sun, and a lot more of like, let's pick a topic and let's actually get to the answer. We're talking about 1,300,225 physical qubits with a logical error rate of 6.73 times, that's where we need to be. And that's a big old project, but I would very much welcome that for the field,
Thank you. Rodney, any closing thoughts? We're at the end of time, and then I would close.
No, listen, I think it was great discussion. I'm intrigued by this grand challenge idea. So maybe if anyone wants to, write in and suggest the target for the grand challenge, right? But it sounds like it needs to be specific. It needs to be something that feels more near-term achievable. It needs to be something that probably feels pre-competitive, and maybe even better if it's something that's good for society. And it needs to be something that clearly can't be done or can't be done well through existing approaches, and needs a quantum solution. So answers on a postcard, please, as they used to say.
Thank you. Okay,
And
so
it would
reach
be
out.
good to have more than one challenges, and then because different systems might be optimized for different challenges, for example.
Great. Perfect. So we can work on this. Thank you for a wonderful panel and doing us a favor, John, especially midnight your time. Thank you so much. We are very grateful to all of you. And it was a great discussion. So we'll follow up for some questions that we didn't manage to answer. And just to say, some of the report will come out around June. Everybody needs to review and provide input, but that's around the time. There was one question. Thank you so much for this. And I wish everybody a great rest of the conference. And thanks, John, Matt, Pete.